Okay, so the purpose of this is to actually illustrate the concept of activation and inactivation and how we actually measure this. So just to reiterate, right, we've got a certain amount of current, oh boy, okay, we have a certain amount of current that's going to go through a channel. We're going to call it, and we're going to use the sodium channel as the example. Okay, a certain amount of sodium current that's going through a membrane with a bunch of channels, of which there are N channels, N sodium channels. Each one of them has a unitary current of a certain amount, as dictated by the difference between the membrane potential and the equilibrium potential for the sodium ions, times the probability of the sodium channels actually being open. Okay, put that sodium up here. Okay. Now, in the notes, I indicated, right, that we are really, when we're talking about gating, we're really talking about the probability of the channel being in the open conformation, right? And it's only in the open conformation if it's not in the closed conformation or the inactivated conformation, okay, at least for sodium channels. And therefore, we want to characterize this in terms of what we call activation and inactivation curves, right? Because this is going to tell us what the extent to which the channels are available for being in the open conformation. Okay, if we just rearrange this equation, we can actually solve for the open probability of the sodium channel, right, which again is related to, this is related to whether or not the channel is in the closed state, which we call the deactivated state, or the inactivated state. Okay, we'll come back to that. And this turns out to be, of course, you can measure this by just measuring the amount of sodium current. What I'm going to do is just bring these two over to this side, divided by the number of channels, times divided by the unitary current. And this unitary current is actually, as we said in class, is actually some constant times the membrane potential minus the reversal potential for sodium. Okay? So we actually have that it's some constant probability of opening is related to some constant times the current that we measure, which is again going to be a function of voltage and time. And we're going to divide that by essentially the driving force here for the sodium channels, and that's actually going to be Vm minus the reversal potential for sodium. Okay, so we're going to measure this in a voltage clamp experiment. We're going to know what this is. We're actually controlling this, and we set up our conditions so that we can actually calculate this. Okay, so how do we go about doing that? Okay, so let's take the case of the sodium channels again. And the easiest way to think about this is using what we call state diagrams or gating schemes. And we know that the channels can actually be in closed conformations from which they can actually transition to an open state or open states. Typically there's only one for most voltage dependent channels. And in the case of sodium channels, they can actually undergo inactivation to an inactivated state, which turns out to be actually a number of different kinds of conformations. And in the case of sodium channels, they can actually transition, they're capable of transitioning directly from the closed state to the active state. And we're going to see that in a moment when we actually do inactivation curve measurements. Okay? So we're going to start by just talking about the process that's involved in closed to open transitions. And what we're going to do is we're going to assay this, and we're going to call this the generation of what we call activation curves. Okay, and the way we do this is actually to start channels off at very negative potential. So I'm going to just redraw that gating scheme here. So it's closed to opened to inactivated. Okay, and if we go to very negative potentials, we can actually force the channels or encourage them to be in this closed conformation. And typically for sodium channels as well as many voltage dependent channels, that turns out to be around minus 120 millivolts. Of course, cells are never at that value, but we can actually control that with a voltage clamp experiment. We're actually going to imagine doing a voltage clamp experiment. Okay, so that allows us to instantaneously change the membrane potential in the fashion shown here, and this can be any voltage. This is what we're going to call the test potential. Okay, and remember what's happening here, right? We've got a cell, we've got a patch electrode here, and we can control that. We can control the voltage inside that cell. And in that cell are a whole bunch of these channels that are just sitting there in a voltage-dependent way, are capable of undergoing different conformations, right, and transitions to different conformations. And then we can actually change the voltage, right? So we can actually change this to, let's say, even a positive value, and we'll see we will actually do steps to even positive membrane potentials, right? And when we do that, of course, these channels are going to undergo conformational changes, and we're going to refer to those conformational changes as the process of activation and inactivation. Okay, so now let's see what happens if we choose our test potentials to different values. Okay, so this number can be a variety of different numbers. And if we were to do this membrane, change this membrane potential from -120 to -70, okay, I'm going to do that in red here. We would start off with no current. This is the zero current level right here. We'd start with no current, and when we actually got to this transition, when we actually stepped to -70, this is sitting at -120 here, we now stepped in the test potential to -70, we would actually find nothing happens. No current. If we step to -60, also no current. Okay. Now, if we were to step to minus 50 millivolts, right? Now we would actually see current. What we find is we'd start off again with zero current because we're at -120. Now we step to -50, and lo and behold, we actually begin to see inward current, but then inactivates. And then on this transition back to the -120, -120 millivolts, we would actually find that there is no change, that the current would actually remain at zero. Okay, if we were to do it at -40, okay, what we would find in that case at -40 is that we would actually pick up more current, it would activate faster, and it would inactivate faster than at -50, but still relatively slow, as we'll see. By relative, I mean relative to the other voltages that we're actually going to use. Okay, so that's -40. Now if we go to -30, we're actually going to get a little bit more current. Okay, it's going to occur more quickly, and it's actually going to inactivate more quickly. Now think about what's going on here. We've actually got more current at -30. The peak current here is larger at -30 than it was at -40. Now remember that our driving force for current going through this channel is going to be Vm minus the reversal potential for sodium. Well, in this case, Vm is going to be either -40, let's say. It turns out this number is actually about 60. So this driving force is going to be -40 minus 60, which is a driving force of -100 millivolts when we're at 40 millivolts. So that would be this one here, gives us a driving force of -100. If we do -30, right, -30 minus 60, that's actually equal to -90 for a driving force. So this is actually a -90 driving force. So we actually have less driving force here, but we have more current. Okay, and why is that? Because we actually have a higher open probability, and we'll actually see how we arrive at that in a moment to actually calculate that. Okay, so now if we actually step to -20, now we know our driving force is going to be about -80, getting even smaller, right? But in the case of sodium channels, they actually will generate more current when you step to -20 than when you step to -30. And they will also undergo a faster inactivation rate, as shown here. Okay. Now if we go to, from here, if we now go to -10 millivolts, what we'll actually see is that the current will actually now decrease. It will actually be a little faster than before, but it will actually decrease. So this is actually now -10 millivolts. Okay, just to point out which one this is. Okay, now, and the reason it's going down now is because now our driving force is only -70. If I were to continue this and go to 0, I would actually find that it goes almost as fast, or as fast. You have a smaller peak, a little faster on inactivation, but not a whole lot. This would be 0. Okay, and I could continue this, and as I go to more and more positive potentials, Now if I go to, I just went to 0 here. Now my driving force is minus 60. If I now go to plus 10 millivolts, okay, I'm going to make that pink. Oh, I'm not going to make that pink. I'm going to use my pencil again. That's minus 50 millivolts, right, as a driving force. And I'm actually going to pick up even less current. I come down here, and it's going to be like this. Okay, and this is going to be my plus 10. Okay, so now the question is, how do we use this information? And we can generate activation curves by recognizing, right, that my open probability is going to be proportional to the current that I measure, in this case the peak current that I measure at whatever voltage I step to, divided by the driving force, which is Vm, whatever that membrane potential is, and those are the ones shown here, right, minus the reversal potential. Okay? All right? So, if we first of all just plot what we call the current voltage relationship, we would actually see here, if we're going to plot the current on this axis and Vm on this axis, what we'd find is it does something like this. And we know this because we just went through it. And this peak turns out to be at about minus 20 millivolts. And this is about minus 20. We'll go to minus 10, it's a little bit less. 0, it's a little bit less. This is minus 30 here, minus 40, minus 50. And we're up to minus 60, so this is minus 50, minus 30, okay? And that's what it looks like. Now if we want to calculate now the probability, the relative probability of the sodium channels being open, and we do this division of the peak current by the driving force, what we find is that it's going to be 0 at minus 70, minus 60 we know got no current, so if we divide 0 current here by any driving force, we're going to get 0. Now at minus 50 we started to pick up a little bit of current. So if we divide that by the driving force is pretty big, so regardless of what current I got, I'm going to get a small number. Minus 40, I have more current through the channel, right, through the channels here. And of course my driving force is actually still relatively large. I'm going to get something that looks like this. At minus 30, it's going to get a little bit larger. At minus 20, it's going to get larger. But now notice here, by the time I get to minus 10, the actual peak current is going down. However, so is the driving force. And when you actually do those calculations, it turns out that these curves start to roll over like this. Okay, and so this actually represents now the probability of the channels opening when we went from minus 120 to whatever membrane potential that we use to activate the channel. Okay, and so we find that these channels start off with 0 probability of actually opening from that very negative membrane potential at these relatively negative potential. And as soon as we get to about minus 50, we start to see the ability of these channels to transition from the closed state to the open state. Okay, and assay that by looking at these peak currents. Now, fortunately, in the case of sodium channels, we have a situation where when they gate from closed to open, this process is fast enough so that the channels are able to open prior to them actually going into the inactivated state. And that's what we saw down here, right? When we saw these channels open and then subsequently close, what we're really seeing is conformational changes from the permissive closed state following depolarization to the open state. Very rapid process takes place in about 1 to 2 milliseconds. And then the subsequent trickling of these channels over into the inactivated conformation, right? Another non-conducting conformation is very distinct from the closed state, right? Because this is now at a depolarized potentials. The channels are no longer in this state. They actually end up completely in this non-conducting state. Okay? But while they're transitioning, we can get an assay of the number of channels that were capable of going from the closed state to the open state by just looking at the peak currents, and again dividing them by the driving force, and now we're getting a measure of how strongly the channels are, how strongly they're driven into the open state from the closed state as a function of their voltage. Okay, so this is actually called the M infinity curve, or in other words, the activation curve. Okay, so that's it for the activation process, and now I'm going to stop and put up another video for the inactivation process.